Hello everyone, and welcome back to our exploration of elementary probability and statistics. Today we're going to be continuing our exploration through some special probability mass functions and introduce two known as the binomial and the multinomial PMS. So let's first off start by defining what a binomial random variable is. So a binomial random variable x is going to represent the number of successes in a finite sequence n of binary independent trials. If x satisfies that, we call that a binomial random variable. So let's just start off with a quick example. Let's assume that you have 5 trials, and I ask you, what is the number of successes that you could have in that sequence of 5 trials? Well, x could be 0 because if you try 5 times, you could fail every single one. You could succeed once, you could succeed twice, 3 times, 4 times, and at most 5, right? So if n is equal to 5, then x ranges from 0 to 5. So if x is equal to 0, then what is the probability that x is equal to 0, right? Which we'll write as px0. So that's going to be the probability of failure, 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 and failure, which is just going to be equal to 1 minus p to the power of 5. But that's kind of boring. So what about x is equal to 1? So that's the probability that x is equal to 1, and we have several different rearrangements of this because that could be failure, 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 and success. That's 1. Or we could have failure, 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 success, and failure. Or all the way down to the last one, if we keep on rearranging in this particular structure, or that. Right, so keep in mind, notice that we have 4 F's and 1 success in every single one of these structures, and we're just rearranging those particular objects. So the number of rearrangements will just be equal to 5 factorial all over 1 factorial times 4 factorial, where 1 is the number of s's and 4 is the number of f's, for which we could write as C51, or we could also write it as C54. Either one is perfectly fine, with C51 being the most common, but 5 factorial over 1 factorial 4 factorial, the more useful structure of that. Because technically speaking, what we have here, 5 just represents the sample size, or the number of trials, 1 corresponds to the number of successes, and 4 corresponds to the number of failures. And this particular structure is going to be very, very useful once we start to extend the binomial into the multinomial case. So if we represent the probability of success as p, and also keep in mind what p represents, p is just going to be representing a percentage and not a ratio, right? So it's not a ratio. For example, in the past you tried you succeeded 4 out of 10 times, therefore this would be equal to 40%. No, we're not focusing on this ratio, so we do not know exactly how many times we tried in the past in order to get this particular number, right? So this probability of success needs to be presented in an exact percentage form, where the number of trials for which that was generated was not known, or the number of successes that we could have is not capped above by some certain amount. Those will be another type of probability mass function, which we'll get into next time. But this probability of success needs to be presented in a percentage form, and where that percentage came from, nobody knows, nor do we care, at least for now. So what is the probability mass function for a binomial random variable? So we're going to rearrange our x successes in our sequence of n trials, and then we're going to have some failures, we're going to have some successes. X is going to be representing the number of successes, and therefore if we try n times with x successes, that means we have n minus x failures. And here x is going to range from 0, 1, 2, all the way down to n, and this object is what we refer to as the binomial probability mass function. So now we have a probability mass function. Now obviously we would like to get our expected value of it. So the expected value of x will be equal to, from definition, the sum from x is equal to 0 to n of x times our probability mass function, which is going to be n factorial, x factorial, m minus x factorial, and then 1 minus p to the m minus x times p to the power of x. And then obviously we're going to do some magic math here, and you probably don't care about that, but if you do, definitely be careful careful in how you simplify that. But what you're actually going to get is just n times p. So that nasty looking mathematical expression actually turns out to be something quite simplistic and beautiful. So the expected value is going to be equal to the number of trials times the probability of success. And similarly, you should be able to find that the variance will be equal to n times the probability of success times the probability of failure, 1 minus p, which some people will represent by q. So if we have these particular structures, we can actually write them in an alternative way, because some people write mu instead of expected value, and that's perfectly okay. So we have mu is equal to n times p, and sigma x, the square root of variance, will be equal to the square root of n times p times 1 minus p. So that's the mean and the standard deviation of a binomial random variable. And we have the probability mass function, n choose x, and then 1 minus p to the n minus x times p to the power of x, where x ranges from 0, 1, all the way down to m. So what does the graph of a binomial distribution look like? There's actually three variations that you could have for binomial random variables. So this horizontal axis is going to be equal to x, and then we're going to have the probability mass functions on the vertical axis. So the number of trials is obviously going to be capped off by m. And let's actually use a focus point of n over 2. Right, so if you have a probability of success of 50%, then you should expect the mass of this probability to be somewhere centered around n over 2. So we're going to have our p is equal to 50%, our p is less than 50%, and then our p is greater than 50%. Take a guess of what you think these curves look like. And keep in mind, they're discrete curves, not continuous curves. So what you're going to have actually is 50% is going to be relatively symmetric around n over 2. Less than 50% is going to be skewed to the right, so it's going to be having a mass more situated on the left-hand side of the distribution. And then for this one, you're going to have a probability that is situated more bigger than n over 2. And also keep in mind, this is a discrete curve. See, these are just a bunch of dots, actually, not a curve. Right? So that's what the binomial probability mass function is, what it can look like, and also the mean and standard deviation of a random variable. Now let's get into a practical example on how this can be used in real life. Suppose that 72% of a population likes cats, and you select a simple random sample of 32 people from it. Before we proceed, it's very important for me to point out that this probability of success, quote unquote, that of liking cats, is a percentage, not a ratio. In the population, we do not necessarily know how many people are in that population, nor do we know the exact number of people that likes cats within that population. Now, what is the expected number of people in your sample of 32 people that likes cats? So let's first off start by defining a couple things. So success is like cats. And the probability of a single person liking cats will be equal to 72%. And let's also define x to be equal to the number of people in our sample of n equals 32 that have a success, that likes cats. Then you should be able to easily justify that x is binomial, right? In particular with n is equal to 32 and p is equal to 72%. So since it is a binomial random variable, we have a shortcut formula for the expected value. So expected value will be equal to n times p. So that's going to be equal to 32 times 72%, which is approximately equal to 24. So we expect somewhere around 24 people in our sample of 32 to like cats. Yes, obviously it's possible that nobody in our sample likes cats. It's possible that everybody in our sample likes cats. But on average, we do expect, if it's a simple random sample, that some people like it and some people don't. In particular, we expect somewhere around 72% of our sample to like cats. Now let's look at another problem. Let's actually switch to the probability world. So what is the probability that exactly 25 people 25 people in your sample, and your sample likes cats. Right, so pretty much what we want was we want the probability that x is equal to 25. So we have a sample of 32, and we want 25 successes, and we don't care about the order of them. Obviously, we're going to have some failures, and we're going to have some successes. We want 25 successes, and we have 32 trials, which means we want 32 minus 25, or 7 failures in that sequence. Once you actually work out that number, you're going to get 0.1232, or approximately a 12% chance that exactly 25 people in your sample likes cats. Let's do an inequality problem just for practice. So what is the probability that at least, let's do 22 people in your sample likes cats? Now, very important is some people are going to ask you questions about not liking cats. View it from the complement, because liking cats and not liking cats are complements of each other. And if you've already defined your x, you don't want to confuse yourself of what x is and the direction and so on. Right? So we want the probability that x is at least 22, so x is greater than or equal to 22, and keep in mind n is equal to 32. So this is bounded above, so we can actually target this directly. So this is going to be equal to the probability that x is equal to 22 plus the probability that x is equal to 23, all the way up to the probability that x is equal to 32, and we just need to add those one by one by one by one and not make any simple mistakes. Now this calculation is a little bit more advanced for some people to do by hand, but if you are using software that has access to summation notation, we can just sum this from 22 to 32, so 22 to 32 of our probability mass function evaluated at k, and once you find that, that's going to be approximately equal to 73%, or 0.7337. Right. So, if you have access to software, you can obviously solve more advanced problems, but nonetheless, that would be how you would find it if you were to do it by hand. Now, before I move on, I just want to mention something, especially if you watched the last video where we discussed the geometric and the negative binomial random variable, because there is one thing that is very, very similar between binomial and negative binomial, aside from them having the word binomial in their names. But binomial and negative binomial look similar in structure, but are very, very different. And I just want to point out why they are very, very different, although their name sounds very, very similar to each other. So we have binomial, right? And then we have negative binomial. So what do they represent? So binomial, x, represents the number of successes in a sequence of n independent binary trials. And x for negative binomial represents the number of trials to get our successes. Right, so x represents the number of successes for binomial, and negative binomial, x represents the number of trials. So it is measuring something completely different. So what's the probability that it takes you, 5 trials until you get 3 successes? That's negative binomial. What's the probability that you get 3 successes in a sequence of 5 trials? That would be binomial. So it's very, very different in terms of the problems that they solve. Now, if you look at the probability mass function for a binomial, which is n choose x times 1 minus p to the m minus x times p to the power of x, and then sit that next to the negative binomial, which is going to be c x minus 1 r minus 1, and then 1 minus p to the x minus r times p to the power of r. Yes, they look very, very similar, but they should never be confused between each other because they're measuring completely different things. Binomial, the number of successes, negative binomial, the number of trials. So make sure you understand what the problem is asking, because you should not be getting these two problems mixed up, although their formulas on the surface do look very, very similar to each other. So now let's see if we can generalize the binomial to a broader class of problems. Firstly, the binomial only applies to binary events, hence the name binomial. So obviously maybe we can extend this to trinomial or tetranomial or generally speaking multinomial probability mass functions. So for binomial probabilities, what we do is we take our probability space omega and partition it into successes and failures, with the probability of success plus the probability of failure obviously being equal to 1 since they are complements of each other. And more importantly, the probability of success and the probability of failure are percentages. Percentages, not ratios. Yes, they are very similar to one another, but how you solve these problems, if you were to say, oh, there's 5 successes and my population size 52, will be solved completely differently. So, for example, if you have the probability of success being equal to 50% and the probability of success being equal to 7 divided by 14, yes, 7 divided by 14 just does map to 0.5, which is 50%, but this problem here can be solved with binomial probability mass functions, but this is not going to be binomial in terms of its solution strategies, but this is for another PMF. So do not worry if you do know extra information about your population. There are functions that will help you solve that for you and get more precise answers. Right? But we're only going to be focusing today on the percentage perspective, binomial and their extensions. So let's suppose that omega is partitioned into more than two events. So if omega is partitioned into more than 2 events, then we're going to be using what is called the multinomial PMF. So let's take, for example, that you partition our probability space omega into 3 events. Let's assume that they're called A, B, and C, with the probability of A being 0.20, the probability of B being equal to 0.50, and the probability of C being equal to 0.30. And again, these are percentages, not ratios. Right? If you have 3 or more events and you have ratios, then there's another distribution that can be used to solve those. All right? So what we're going to do is we're going to do a simple random sample of n from omega. And let's assume that we want NA, MB, and NC from each A, B, and C respectively, with NA plus NB plus NC being equal to M. Right? So for binomial, to sort of see if we can see a pattern here, we had that the probability that x is equal to x was equal to the probability that our sample has a certain number of successes and a certain number of failures within that particular sample, right? So this is almost like a vector, but it's nonetheless a sample structure, right? So we have XS successes and XF failures. And what did that come out to? Was just going to be our sample size divided by the number of successes factorial times the number of failures factorial, and then multiplied by PS to the number of successes times PF to the number of failures. Right? And keep in mind, those are going to be percentages, not ratios. And we can obviously flip this around because it doesn't really matter the order. So we have PF times the number of failures, and then PS to the number of successes. So this is the same binomial probability mass function. You're like, why do you change the notation? Isn't that going to be complicating things? No, not necessarily, because notice that this is actually the same exact thing. Because if x corresponds to the number of successes, then we're going to have x factorial, and then since we have only 2 events, n minus x is going to be the number of failures. The probability of failure is going to be 1 minus p to the n minus x x times p to the power of x. So it is exactly the same exact formula. The only difference is when you try to extend it to more than 2 events, then this orange representation of the binomial isn't going to be very, very useful. So how are we going to extend this to the multinomial case? Obviously, the former perspective is actually going to be useful. So this is the multinomial case. So let's assume that our sample S needs to be of the structure A, B, 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 C, 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 and C. Right? So what is the probability that I get 2 A's, 3 B's, and 4 C's? So what I have here is the number of A's is equal to 2, the number of B's is equal to 3, and the number of C's is going to be equal to 4. Therefore, our sample size was 2 plus 3 plus 4, which is equal to 9. So you take a sample of size 9 from your population. What is the probability that you get 2 A's, 3 B's, and the rest C's, which would be equal to 4? So how many rearrangements of these are there possible? Or are there? Because we don't really care, where these A's, B's, and C's are. As long as we have 2 A's, 3 B's, and the rest C's, it doesn't really matter. So the number of rearrangements will be equal to, well, if they're all different, then there's going to be 9 factorial of them. And now these 2 factorial, 3 factorial, and 4 factorial ABC rearrangements are not equal. So we need not consider that, and you should be able to verify that it comes out to approximately 1260. So what is the probability of us getting this event? So the probability of us having this particular sample structure, xa is equal to 2, xb is equal to 3, xc is equal to 4, and a sample of size 9, this is going to be equal to all rearrangements of those probabilities. So that's going to be 9 factorial all over 2 factorial, 3 factorial, 4 factorial, multiplied by the probability of a to the power of 2, the probability of b to the power of 3, times the probability of c to the power of 4, and that would be your probability. And then we can bring back our probabilities that we mentioned before for A, B, and C, provided that they are in percentage form. And that's going to be 20% to the power of 2, 50% to the power of 3, and 30% to the power of 4. And make sure they are in the same exact order for which they are presented to you. And you should find out that's approximately equal to 0.0510. All right? So that's how you find probabilities with multinomial structures. So what about the expected number of A's, B's, and C's in our sample? Take a guess of how we would find this. So the expected value of the number of A's in our sample would be equal to our sample size times the probability of A. And how would you find the expected number of B's in our sample? So the expected number of B's in your sample and the expected number of C's in your sample. That's going to be equal to n times PB, and then finally n times PC, which for our PA, PB, PC, and n values, that's going to be approximately 1.8 A's, approximately 4.5 B's, and approximately 2.7 C's. Right? And it's very, very important to note that the sum here will always be equal to m. And also, in case you're curious, you can find the variance of AK to be equal to n times pk times 1 minus pk. Pretty much has the same exact structure, just like, binomial is n times p. Here we have n times pk, and the variance of xk will follow that of binomial. It's just, n pk times the probability of failure for that particular structure. Now that we pretty much know how to solve multinomial problems, let's phrase this into a more real-life context. Suppose a population is partitioned into 4 different moods: happy, sad, depressed, and neutral. And you estimate there to be approximately 43% of the population is happy, 24% of the population is sad, 5% of the population is depressed. Since it is partitioned, the sum of all of these should be equal to 100%. So what do you think the percentage of neutral people are going to be equal to? You should be able to find that that's going to be equal to 28%. Right? And again, it's very, very important that these are percentages, not ratios. In particular, if they were ratios, we would have to find 1, the population size, which in practice is usually not known, and then 2, the exact number of happy, sad, depressed, and neutral people within that large population size, which is again super difficult. But if you do happen to have that information, there are distributions that are out there that are going to be able to solve that with more precision, which we'll get into in the next video. So now what I want to do is go into this population and select a simple random sample of, let's say, 50 people. So if we select a simple random sample of 50 people, we should be able to estimate the expected number of happy, sad, depressed, and neutral people within our population, or within our sample. So the expected number of happy people, the expected number of sad people, the expected number of really depressed people, and then the expected number of neutral people within our sample. So our sample is of size 50, so 50, 50, 50, 50, and then you just need to multiply by the percentage of each of those people in our population. So 43%, 24%, 5%, and 28%, and you're going to find that to be approximately equal to 21.5, 12, 2.5, and 14. So for example, in your sample, you do expect there to be only 2.5, somewhere between 2 and 3 people in your sample that's depressed. So if you find that 48 people in your sample of 50 are depressed, then 1, maybe your sample is not a simple random sample, or 2, maybe these percentages are wrong or potentially outdated, and maybe these percentage estimates are wrong, and maybe they're based on wrong data or wrong research. So there's a lot of things you could do as a result from the experimental design process. Right, so we expect these particular numbers in our sample, but we of course can add probability questions. So what's the probability that our sample of size 50 has the following structure, right? So we have the number of happy people, the number of sad people, the number of super depressed people, and the number of neutral people within our sample. Right? And since we have a sample size 50, then the sum of these numbers that I'm about to state have to add up to 50. So if I want 22 happy people, 13 sad people, and 11 neutral people in my sample, how many depressed people can be in our sample? You should be able to find that that is going to be equal to 4. So technically speaking, if I tell you the sample size, only 3 of these pieces of information need to be given to you. So let's rearrange all of these people because we don't care about the order as long as the number of their categories are there. That's really all we care about. So we're going to have 50 factorial divided by, so then we're going to have our 20 happy people rearrangements, our sad people rearranged, our depressed people rearranged, and then our neutral people rearranged. And then what we're going to have is our probabilities raised to the power of the numbers that we want. So our population is 43% happy, 24% sad, 5% depressed, and 28% neutral. And within our sample, we want 22, 13, 4, and 11 people in our sample to have that. So once you actually work out this number, then this is going to be equal to approximately 0.0018 or 18% chance. So what is the interpretation of this number? So therefore, there's an approximately, and that's 0.18, not 18%. So there's an approximate 0.18% chance of our sample having this particular, we can call it emotional profile. Emotional, some people also say mood profile. Right? And that's how you can use a multinomial to sort of assess that. So in this video, we discussed the binomial distribution, which is only associated to binary structures for samples. And then we also extended that to multinomial distributions, which can give you probabilities for structures of samples where your partition is not necessarily binary, but it could consist of maybe 5, 3, or 20 different subsets or substructures in your population, right? And very, very important, all these probabilities need to be represented in percentages, not not ratios. So I hope you enjoyed this video, and I'll see you in the next one. Take care.